Does the microphone work? Does it work well? All right. Oh, does it work well? Okay. No? Higher? Let's see. Up here? Or sorry. Is it better now? Better? All right, thank you very much. Yeah. Well, thanks for coming today. I'd love to talk about the work we've done with my group on Phonon-assisted optical properties in materials and this new implementation on ETW. So first of all, a few references for you. If you're in the field of optics, I recommend the following books for you. The Oxford Master Series by Mark Fox is a wonderful introduction to the topic of optics in general. Another one, very interesting for technical aspects is the Bassani-Paravicini book. It has very detailed equations for everything, as long as these three papers are very handy. Oh, thank you. Thanks so much. Plastic, much better. All right, so first of all, the motivation. Why should we worry about phonon-assisted optics? And a very strong motivation is silicon itself. Perhaps one of the most important materials in history and definitely the most important semiconductor. If you look at its direct absorption of, here's the occupied valence band, conduction band, occupied states and empty states. When we send the photon in, electrons absorb the photon and go from the valence to the conduction band. That's a direct absorption, and it's well understood. Today we have very good spectra. And here's an example from the Berkeley GW code. The dots you see here are experimental data for the absorption spectral silicon, the dielectric function, as a function of photon energy. And you see that the curves without excitons, that's the GW level. You get the right peak positions, the peak heights don't come out as correctly. But once you include excitons, you get an excellent agreement for the peak position and the peak heights at the same time. And not only that, also this work by Marini also shows that you can also determine the spectra, send spectra as a function of temperature. These vibration can broaden the absorption and tell you how the spectra in ultraviolet change with temperature as well. So silicon we do understand very well. If you notice though, all these absorption calculations occur in the ultraviolet. And while in the visible spectrum, the absorption you would get from it, if you do a direct calculation, will be 0. And the reason is that we know though that silicon does absorb visible light. It's not transparent. Its indirect gap is 1.2 electron volts, while the minimum direct gap is 3.4 eV. So you only get direct transitions when your photon energy is in the ultraviolet. It's impossible for silicon to absorb in the visible. To absorb across the indirect gap, you also need the assistance of phonons. You need some extra mechanism to provide momentum and conserve the overall energy and momentum in the process. And actually, this kind of mechanism is what enables silicon solar cells to work. Without phonons, silicon will be transparent like glass. So we want to understand this mechanism in materials in general. All right, so when we come back to discuss a little bit about linear optics, just to introduce the coefficients that we're going to calculate today. Linear optics primarily deals with refraction and absorption, right? And here's an example of Snell's law. The refractive index tells you how light bends when it crosses from one material to the other. And absorption, here's an example of the laser pointer pointed to a solution, and you see this exponential decay of the intensity of the beam as it gets absorbed in the material. Okay, and the absorption is a function of position, in this case, the depth in this solution, decays exponentially, and the exponent is alpha times the position. And alpha is the coefficient we're interested in, the absorption coefficient. It's units, as you see, it multiplies length, so it has to be inverse length, and usually measured in inverse centimeters. And when you talk about the material that's a strong absorber, like a gallium arsenide, solar cell or so, values you get about 10 to the 5 to 10 to the 6. And if you invert that, you get the characteristic length scale over which light absorption happens. So for a direct gap material, typically 1 micron is the distance over which you absorb most of the light that passes through it. Okay, so these are the coefficients we're focused on, and these are numbers to keep in mind about what is strong and what is weak. Okay. All right, so So to generalize, to combine those two, we lump them together in what we call the complex refractive index. It has the real and the imaginary part. The real part dictates propagation of light. The imaginary part, imaginary component, dictates the dissipation of light, the absorption. Okay. You also talk about the complex dielectric function. Again, the real part presents the screening and propagation, while epsilon2, the imaginary component, is the absorption that we saw earlier in those plots. The two of them are, of course, connected. In the simplest approximation, one is the square root of the other, but if you want the full equation, it's right here. So n and k depend on epsilon2 through these two equations, right? And last, if you want to find the absorption coefficient, again, in units of inverse length, it's directly proportional to the kappa, the imaginary part of the refractive index. Okay, so you multiply by omega and c, and then you have this coefficient you can then go and measure experimentally in an optical experiment. Okay, so these are the parameters we'll focus on in our calculations. Okay, now if you go back to the early theories of light absorption materials, in this case a metal, you look into the semi-classical theory developed by Drude that was even actually older than quantum mechanics. And the way you would do this is you would write down a Newton equation, effective mass times acceleration is equal to, here's the electrons in the material, then you apply an electric field, and they feel forced by the field. And at the same time, they scatter, right? Every so often, with this time scale tau, those electrons scatter in the material and change their momentum. And you must have seen this problem. If you apply a static electric field, you can derive the conductivity of the material. That relates to mobility calculations we discussed earlier in the school with this parameter tau. If you also studied the same problem under the influence of an alternating field, an AC field, you can also derive an equation for the absorption coefficient. Okay, and again, directly proportional to tau. And the reason is that if those electrons can't scatter, then they would not absorb light. Okay, you can see this because this is a free electron, basically, parabolic band. There's no way to conserve energy and momentum in light absorption in a parabolic band. You must have a phonon to give the overall conservation of energy. And also, once this theory was derived, this tau parameter was phenomenological. You basically measure a spectrum, say the absorption in a metal, and then you find the tau parameter that makes your equation fit the spectrum. But today, of course, we can calculate this tau, and that's what we are going to do. We need to calculate, we need to study this scattering of electrons by phonons, by defects, by any impurity you might have in your material, and be able to predict absorption. To do it right, of course, you have to go back to quantum mechanics. You can't use Drude theory for a predictive theory. Okay. So the way we study optics is we use perturbation theory. We assume the light perturbation is weak. We work in the regime of linear optics, where the field is not too strong to damage the material or cause linear effects. We assume that we have our arbitrary state, our starting point, is what comes out of a DFT calculation. You also may either correct it to get GW corrections to your band gaps, but that will be your starting point. You have a set of initial non-interacting electrons would occupy the quantum orbitals and their eigenvalues. And then what you do is you actor them with the electron-photon Hamiltonian. You assume you're sending in an electromagnetic field, so it's characterized by the vector potential A times the momentum operator P. Okay. In some sense, this is the dipole approximation. It's like the electric field coupled to the dipole moments in your material, but it's easier to work in the momentum space because extended solids don't have a well-defined position operator. It needs more complex math to work it out. Okay, so how we find the optical transitions, the rate for optical transitions as a function of time. So it comes out from the well-known Fermi's-Gordon rule. The probability per unit time that the optical transition will occur from state I to state F, your initial to final state, is 2 pi over h bar, the square of the matrix element of the perturbing Hamiltonian times the delta function, which ensures that we conserve energy. The initial and the final state must be the same. Okay. Now, what are the initial and final states? In the initial state, you can assume that you have electron in some valence band and a wave vector k. Your final state, now your electron has gone to a different band, the conduction band, and also you have the energy of the photon. This is the case of emission. In case of absorption, you have the h bar omega in the initial state. Electron plus photon gives you the excited state electron. Okay. So how then do you connect this microscopic quantum property to a macroscopic measurable quantity? Okay, the absorbed power, the power that your system absorbs per unit time. This is the probability for a transition of a given electron from a given initial state to a given final state. Of course, these states have to be, the initial state has to be occupied and the final state has to be empty, according to Fermi statistics. So you need this prefactor. And then you need to sum over all possible initial and final states in your system. And that this part tells you how many electrons go from the valence to the conduction band per unit time. You multiply by h bar omega, the energy of each of the photons getting absorbed, and that's how you get how much power is coming into your system. Okay, so this is how much power is absorbed by your system. Of course, this quantity P contains the electron-photon Hamiltonian, which then depends on the amplitude of the electric field. So to normalize, we also have to factor in what's the incident power coming in. So here you know the refractive index of the material, the amplitude of the vector potential, and the optical parameters. So once you know the power coming in, the power getting absorbed, you can derive the equation for the absorption coefficient, right? It's simply this ratio. Okay. And if we translate this to quantum mechanics, okay, here what we get. We get this prefactor that involves constants, optical parameters of the material, like the refractive index. And then here's the quantum mechanics. We have a sum over initial state band, final state band, and the Brilliant zone index K. The parameters that enter are the Fermi occupation factors. Again, we can only go from an occupied to an empty state. If both are occupied, the Pauli exclusion principle forbids an optical transition. And then you have this property, the optical matrix elements between your initial and your final state. But also you need to take into account the polarization of the light you're sending in. For a plane wave polarized light, the lambda is say, along the x or the y or the z direction, so you correspondingly take the x or the y or the z component of the momentum operator. Last, you have to multiply by the energy conserving delta function. So your final state has to be the initial plus the photon energy. So this acts like a density of states. The more states you have, the more probable it is to absorb the photon. Okay. And of course, if you know the absorption coefficient, you can also find the imaginary part of the dielectric function. Again, a similar equation with a different prefactor. Otherwise, the same quantities come in. And once you know the imaginary part, you can switch to the real part and find the screening properties or the refractive index through the Kramer-Kronig relation. And if you do that, you get this equation. So instead of a delta function, now you have these energy denominators. And one thing to note here is that in the imaginary part, because you conserve energy, you don't need to worry about states close to your photon energy. If your photon energy doesn't match an energy of a transition, you won't have absorption. But when it comes to refraction, this sum can basically go all the way to infinity. You have to sum over states that are occupied even to high energies. So this sum is not limited to near the band edge. You have to do a summation over many empty states. So here we'll focus on absorption. We'll focus on the near edge properties. But you can do this calculation as well. You just have to include a lot more bands than you would do for absorption. Okay. All right. Now, how do we put phonons in the picture, right? So far, we just talked about a single photon, linear material, and look at direct optics. To do phonons, we also need to go to secondary perturbation theory because we now have two perturbations coming in. Okay. We have the electron-photon interaction, but also the electron-phonon interaction. And we need to consider both of them at the same time. So we have to generalize Fermi's golden rule to go to second order. Again, 2 pi over h bar as before, the energy conserving delta function. And now the matrix element, we have to generalize it. Okay, we have to take our perturbation to second order. And this perturbation, and also divide. So this causes transition from our initial state to some intermediate state, and from intermediate state, the perturbation causes transition to the final state. And we have to sum over all those possible intermediate states to get a total rate. Okay. Now, each of these H perturbation Hamiltonians contains the electron-photon part and the electron-phonon part. So here what we have really 4 terms, okay? Electron-photon 2 times, or electron-phonon 2 times, or the cross terms, where one of them is the photon, the other is the phonon, like this one. So if you want to study phonon-assisted absorption, we need to keep the cross terms only. The other 2 terms is either 2 photon absorption or 2 phonon absorption. Okay, so here's what you get. Either your electron emits the phonon first and then absorbs the photon, or the other way around, first the photon and then the phonon. And because we can't distinguish these 2 processes, these are microscopically indistinguishable, we need to take into account quantum interference between them as well. So we first sum and then square. Okay, just like a double-slit experiment, first we need to sum the amplitude and then square the total amplitude combined. Okay. All right. So then, how does this translate to equations relating to constant eigenstates and energies? Well, here it is. Again, our absorption coefficient alpha is given in terms of constant prefactors, and then a sum over initial and final states. And now notice we go from band I to band J, starting from wave vector k, and we go to wave vector k plus q. And here it is. Here's how we conserve energy, right? Your final state, the electron at J and K plus Q, is equal to the initial electron energy plus the photon energy, or plus minus the energy of a phonon, because it can be either phonon absorption or phonon emission. And what changed, so this changed with respect to direct absorption. The other thing that changed is also the matrix element, right? Now, our matrix element is not just a momentum operator. We have to generalize it to account also for electron-phonon coupling. And again, because we talk about 2 ways to start from initial state to go to the final state, we have to account for 2 possible paths, where in path they label as S1, the electron absorbs the photon first and then emits the phonon, or emits the and path S2, the electron emits the phonon first and then absorbs the light. Okay, so what comes in here is you have the optical matrix element between the initial state I and band M times electron-phonon coupling in the conduction band, divided by this energy of the intermediate state. And the energy here is the total energy, combined energy of electrons plus photons plus phonons. So your initial state, your intermediate state is here. Your initial is the electron plus the photon that has been absorbed yet. For path S2, you first emit the phonon, followed by light absorption at the other at K plus Q. And now the intermediate state involves the absorption or emission of a phonon. Okay, there's also a statistic factor P here, which accounts for the occupation numbers. Again, we must ensure that we go from an occupied state to an unoccupied state. You can't go between 2 occupied states, of course, or 2 empty states. But we also need to multiply by the phonon occupation numbers, the Bose-Einstein occupations. The upper sign corresponds to phonon emission. So here we have n+1. So phonon emission is possible even at 0 temperature. Even if you don't have phonons, you can always emit a phonon. The minus sign cancels this term, so you just get simply NQ. So in that case, the absorption of phonons is proportional to how many phonons you have. Okay. And last one more comment about this sum M over intermediate states. So you start from an occupied state, you go to an empty state. What should the M state be? Turns out it should be all states, both occupied and empty. So an electron can even go down in the valence band, and then electron from coupled to the conduction band. How is this possible? It's possible because this is just a virtual process. This is a mathematical process that it's, for convenience, we draw it this way. In fact, the intermediate state does not have to conserve energy and doesn't have to even be occupied or empty. Have a question? Oh, you say if you have more than 1 phonon in the process? Is that, mm-hmm.
Okay, so what electron should absorb 1 phonon is 1 over 2.
Oh. Oh, you mean this term, right? Yeah, so the plus minus 1 over 2 is, if it's plus 1, it is the plus sign, this becomes 1, right? If it's the minus sign, it becomes 0. So it's either 1 or 0. It's just a mathematical compact notation. You have 2 choices, right? Either it's 0 for phonon absorption or 1 for phonon emission, right? And so to make the binary choice, we write like this. So this is either 1 or 0. It's never 1/2. You're right. Yeah. Okay. Yeah, and of course you can generalize this to have more than one phonon, more than one photon. You can go to third or higher orders of perturbation theory. You can generalize this method. Okay, so basically, but these are the key equations we want to implement to study Phonon-assisted optics. All right. Now, I want to emphasize why this sum is challenging, why it's not as routine as it's been. There are few calculations for Phonon-assisted optics, and here's the reason. If you want to study direct absorption, then you have a single sum over a k points, right? So you have to, for each k point, you sum over bands, and then you do a sum over your entire Brillouin zone, right? And that you can do quite easily these days. You can even interpolate them with Wannier 90 and both the energies and the matrix elements and do it very efficiently for very fine meshes. When it comes down to indirect absorption, though, you have to sum both over all possible initial states and all final states. This double K sum is what makes it computationally very expensive. So try to approach it with a brute force way, just brute force calculate matrix elements, is going to be very, very challenging. To give an idea, for a case of silicon, if you're going to use an energy resolution of 30 millieV to get a good spectrum, to converge, you need a grid of 24 by 24 by 24 K points. And that is both for the initial and the final K points. And if you account for all possible combinations, that gives you about 200 million combinations. So even though calculating one of these diagrams is relatively easy, it takes less than an hour for silicon, if you multiply by 200 million, that's a lot. Okay, that's why trying to approach in a brute force way is basically hopeless. And that's where Wannier interpolation comes in. This is really one of the examples where the power of Wannier interpolation evidences itself. So again, here we use maximally localized Wannier functions to convert to the localized basis. And this way we can have a localized basis set that doesn't interact in the long range. And we can use it to interpolate energies and optical matrix elements. That's what happens in Wannier 90. But the power of EPWs can also do the same thing for the Electron-Phonon coupling matrix elements. So let me go back one step again. So the ingredients we need here is we need optical matrix elements, Electron-Phonon matrix elements, phonon frequencies, and electron eigenvalues. Okay, the rest is summing them up. So having them from the two codes allows us to implement these equations and in a very efficient and computationally not very demanding way. And one note here is that the current version we implement the code, the optical matrix elements are those of the momentum operator. I want to make a comment here in that when you have a pseudopotential, the momentum operator is not the right operator to use. We have to use the velocity operator that is independent of your pseudopotential. And we're working on changing that. The two of them typically differ by a small factor, but we will have eventually velocity implemented soon as well. And because the velocity can be interpolated with the Wannier basis as well. All right, let me make a comment also about what you expect to find when you do a calculation for direct versus Phonon-assisted absorption. And I want to make a note here about experiment. How does experiment know, if you do an experiment, how would you know if your material has a direct gap or an indirect gap? And the answer is you do what we call a Tauk plot. Tauk, the name of the person who invented the method. So if you look at absorption very near the band edge, you will find that for direct absorption, the absorption coefficient is proportional to photon energy minus the band gap to the 1/2 power. This is basically the density of states, right? Divided by omega. So what experimentalists do is they measure the absorption coefficient, multiply by omega, and then take the square of the whole thing. And the answer is you get a linear relationship with respect to the photon energy. So if you plot alpha omega square versus h bar omega, you should get a straight line. Okay, and here's an example here. Here's an experiment for thin selenide nanosheets. I like this plot because it shows both approaches. So on the one hand, you have this quantity f of r, which is a proxy for the absorption coefficient, times h bar omega. You square the whole thing, you get this straight line. So you extend it to well across the zero of the x-axis, and that will be your direct band gap, right? Where this line intersects the x-axis, that's the direct gap. Now, when you have indirect absorption, though, this absorption coefficient is proportional to, again, the photon energy minus the indirect gap plus minus a phonon frequency. And this whole thing now, it is squared. It's not a square, but a square here because the density of states are independent and divided by omega. So now, if you combine alpha times omega and raise not to the square, but to the 1/2 power, you'll get your straight line again. So here's what happens in these curves. These are the exact same data as before, except now we plot the absorption times h bar omega and take the square root of that. And again, you see these straight line segments extending to 0 allows us to get the indirect gap. And of course, it has to be smaller than the direct gap in general. Okay. So in this material, it's direct gap, and here it's indirect gap. And that's how we can tell them experimentally. Okay. Notice though here that the absorption, in the case of indirect absorption, has two onsets. You can have the phonon absorption term as well as the phonon emission term, and the two of them will take off at different energies, plus minus the energy of the phonon that dominates the absorption. Okay, and because you have these two separate terms. All right, so after discussing this, I want to show you the calculated results for the absorption onset of silicon. Okay, again, here's the absorption coefficient of silicon as a function of the photon energy, and now we have the indirect band gap. Okay, so again, absorption starts around the value of the indirect band gap around 1.2 electron volts. And notice here, this is a tau plot that I discussed earlier. We take the absorption coefficient multiplied by the photon energy and raise to the 1/2 power. So this is why we do this. This combination should give us straight lines. And you see that. Let's go first to low temperature. So again, you see a straight line coming from phonon emission, another straight line here coming from phonon absorption. When you're at low temperature, of course, what dominates is the phonon emission. That's why it's much stronger. And phonon absorption is a weak contribution. And the difference in these two onsets is the phonon energy involved in the transition. And what happens now when you increase the temperature? Phonon emission, you see, remains kind of constant. It's not very sensitive, right? It's proportional to n+1. And at low temperature, the +1 term dominates. Okay, but the phonon absorption term becomes progressively stronger and stronger with increasing temperature. The reason is that this term is proportional to NQ, and the number of phonons increase with temperature approximately linearly for acoustic phonons. So in the limit where, when you go to at 0 temperature, you don't have phonon absorption, and in the limit of infinite temperature, both of them are equally important and equal to each other because absorbing and emitting a phonon at infinite temperature is equally probable. So that gives you an example of a comparison of theory to experiment as a function of temperature for the spectra. And I also want to make a note here that when we do this calculation, we didn't account for the fact that the band gap depends on temperature. So we have to shift those onsets to match the onset of the spectra. But you see here the scale is on the order of 0.1 electron volts. And that's, as we discussed yesterday, this is the characteristic scale of how temperature changes your band gap over this range. Okay, so besides this constant shift, the spectra are in very good agreement with what we see in experiment, and they explain the temperature dependence and the frequency dependence. Okay, now this calculation you can also do by using simple models, let's say. But you can get a constant optical matrix element and a constant electron-phonon matrix element. You'll be able to do this even without heavy calculations. But where you really need heavy calculations for is when it comes to calculating the absorption spectrum in the visible range. Okay, and now talking about photon energies between the indirect gap almost to the direct gap, and that covers the entire visible spectrum. And here it's really when the power of the Wannier interpolation comes in, because now we have transition from every possible issue to every possible final state, and that this become very hard to account for with simple models. And that's why the power of ab initio emerges. And again, here we see a very good agreement with experiment over many orders of magnitude for all those frequencies. I want to mention again that we had to shift the origin because we don't account for temperature dependence of the band structure. But besides this constant factor, you see that the spectra agree with experiment. And today we have the tools to account for this energy shift, and we'll get much more predictive power. All right. So this is about silicon. I want to mention another system where phonon-assisted absorption matters, and that is laser diodes, like the point that I'm showing you. For example, blue ray lasers, which are actually violet, emit at 405 nanometers, based on gallium nitride. We use them for optical storage, for laser projectors. And today we want to develop a powerful green laser so we can combine a red, a green, and a blue laser to make projectors that can fit in 1 cubic centimeter, say inside your cell phone instead of these bulky objects. One limitation there is this kind of absorption. I'll show you why. So here's a theorist view of an LED or a laser. So we make them, so what we have is we start with a quantum well of the material that we want to emit light, in this case, indium gallium nitride alloys with a bandgap, say, green or violet. And we sandwich between P and N type contacts, like gallium nitride. We connect a battery, and the battery takes an electron from the valence band of the P-type material and moves to the conduction band of the N-type. Now, those electrons and holes fall into the quantum well because it's a low energy state, where they combine and emit light. So that's what we want to happen in our LED or our laser. So in this actual structure, we have more than one quantum well between the P-type and the N-type layers. So in LED, we want to create those photons, get them out as fast as possible, so we design our structure to get light out easily. But when you make a laser, what you want to do is you want those photons to bounce back and forth many, many times and get amplified, right? What we want to happen is the following. We know about absorption, right? You send photons in a material, and the photons dissipate by exciting electrons hole pairs across the bandgap or another between two states. And that's the Weir-Lambert law we discussed earlier. But here, though, in the quantum wells, we have lots of excited electron hole pairs, and what you get there is gain. And one photon gets amplified by stimulating recombination, and so this positive quantity, G, is a positive number. It tells you how your signal gets amplified as it propagates to the material. In a laser, both of these things happen, both absorption and gain. Of course, gain is what we want, absorption, we don't want it. So in the quantum wells, you have primarily gain. But what happens is your photons don't live here. They have a distribution over the structure. This is the distribution of the electric field of the optical mode. And so they leak into these doped regions where they may get absorbed. And that's what I want to discuss. I want to discuss the process of free carrier absorption. Okay. Now, this is not across the bandgap, right? So here we have a wide bandgap semiconductor like gallium nitride, and the light of the laser is not enough to excite across the gap. What can happen, though, is that here we have lots of free carriers, either free electrons at the bottom of the conduction band or free holes at the top of the valence band. Okay. And in this case, direct absorption is not possible. For holes, for example, there are no states for them to be excited to. For electrons, there is a state, but it's a type of forbidden transition, so it's a very weak absorption. Once you factor in phonons, though, then those free electrons that you have in the conduction band can absorb the light and go to a different state in this intra-band process mediated by both a phonon and a photon. And that's possible for every photon energy. So that can be a source of loss if you have a doped semiconductor. So again, we did the calculation for Phonon-assisted free carrier absorption. Again, now we're focusing on these kind of intra-band processes between electrons in the bottom of the band to higher states. And we found the absorption cross-section. Absorption cross-section, why? The absorption coefficient here is proportional to how many carriers you have, and the proportionality constant is this cross-section. This is a weak process. To give an idea how weak it is, if you have 10 to 19 carriers, which is actually quite high, it's typical for lasers under operating conditions, your coefficient as an order of magnitude is about 10 inverse centimeters. To translate this into a length, it means that you expect a strong absorption over a length scale of 1 over 10 centimeters, about 1 millimeter. That's a scale you would absorb light at. And contrast this to a direct gap material where it's 10,000 or 105,000 stronger absorption, and light gets absorbed in a micron. So this process, of course, is weak. And one of the reasons, of course, that you don't have so many electrons, right? You only have 10 to 19 electrons to absorb light. It turns out, though, because photons in lasers bounce back and forth many, many times, the mean free path becomes hundreds of microns. So it starts to become comparable to the 1 millimeter we discussed earlier. So this process turns out to be quite important for lasers. And one last comment is that you can absorb light by your free holes and or free electrons, but you can also absorb light by bound holes or bound electrons, like dopants in a semiconductor. And And the important thing about gallium nitride is that it has lots of these non-ionized holes, which are still bound to their acceptors. It's very hard to p-type dope gallium nitride. It's done, but actually that was what held the field back for many years. That was the discovery that led to the Nobel Prize for blue LEDs, actually the ability to p-type dope gallium nitride. So what we found in our calculations is that because you have these holes bound to magnesium, they can cause absorption loss in the p-type contacts of lasers, and that is the reason why you lose a lot of those photons inside the laser. Order of magnitude estimates tell you that in a green laser pointer, you would lose about half the light in this absorption instead of getting it out of your laser. So it's a significant source of loss. And it's more important as you go to longer wavelengths, and that's one of the reasons that it's still challenging to make powerful green lasers with direct emission. Most green laser pointers today use a frequency doubling of the infrared laser to give you green light. But the work is being done to make direct lasers that can be as efficient as red or violet ones. Okay. Another thing where light absorption can, another case of Phonon-assisted absorption is transparent conductors. Again, this is another case of absorption by free carriers. So conducting a transparent, you want to make a transparent conductor when you want to make an electrical device like a solar cell, an LED, or a cell phone display that conducts electricity but is transparent to light. So if you want to use a smartphone, you can touch the screen and send commands to your system while you still being able to see your screen. It's because it's coated by a transparent contact like indium tin oxide or tin oxide or zinc oxide. So what's special with these materials? They have wide band gaps. Their band gap is at least equal to the UV energy of 3.4 electron volts, but they're doped. They're heavily doped oxides, so free electrons in the conduction band are those what give you conductivity. So if you look at the band diagram, of course, it's impossible to absorb visible light across the band gap because the band gap is too wide. There's no states for the electrons to go to. And if you look at direct absorption of these doped carriers, again, most of the time there's no states to go to. But if you factor in phonons, then light absorption becomes possible. And that's important because it tells us the fundamental transparency limit of these materials. So it tells you how transparent can a transparent conducting oxide be? Well, here's the answer. If you calculate this properly, you will find the ultimate limit. And we do this for n-type doped tin oxide. And what we got is we got a curve that looks like this. Of course, the crystal is anisotropic, so we have two different absorption spectra for two different directions. And what you see is that surprisingly, this material is most transparent in the visible, which is a very nice coincidence. As you go towards the UV, you get more light absorption, but also as you go to the infrared, this Phonon-assisted absorption by free carriers becomes exponentially more important as well. So it's a power law as well. This is log scale. So this tells what the fundamental transparency limits in those devices. So if you want to dope them or to get more conductivity, you have to pay a price that they're going to be stronger absorbers as well. So it may contribute to a loss in the device. All right. And going back to silicon, this free carrier absorption process can also occur in silicon, and that may actually matter for solar cells. Because to make a solar cell made of silicon, you have to make a p-n junction. So before your light actually gets absorbed in the junction itself, it has to pass through a heavily doped p or n-type region, where again, you have free carriers, and those free carriers can absorb the light. And so there's a competition here. Will your photons get absorbed across the band gap and give you current, or will they be absorbed within the conduction band and then eventually become heat? Okay. And so what happens here is you can have actually both processes in silicon. You can have both a direct process between these two bands, or you can have a Phonon-assisted process through this intra-band mechanism. Okay. So here are results. We examine many mechanisms. We examine the direct absorption, Phonon-assisted, impurity-assisted, as well as the dissipative behavior. It turns out all of them contribute. All of them give you some contribution in the visible and in the infrared. And when we sum them all up to compare to experiment in the infrared range, because experiment, you can distinguish, here you have absorption across the gap and masks the experimental data, but in the infrared, we have reliable data, we see that our theory is again in very good agreement with experiment, and also explains why this shoulder feature happens. This shoulder is coming basically from the direct peak. At this energy here corresponds to the difference of energy between the two conduction bands, and that gives you this slight shoulder behavior, as well as the monotonic increase. So overall, we trust that these methods give very good results compared to experiment, and can explain what happens in doped silicon solar cell. Right. Other groups have also used this method to study metals, because in a metal as well, again, in a metal, I'm not sure this is silver. I'm not sure what the band, which of the metals is this one. But again, you see that direct absorption becomes possible only from the D band to the S band, and only once you factor in phonons, you can have absorption in the infrared and longer wavelengths. And this kind of absorption mechanism is what gives you the dissipative Plasmon energy loss in metals, right? The dissipation rate directly proportional to the imaginary photoelectric function. And again, there is a strong Phonon contribution. So you see here similar equations to the one that matter for Phonon-assisted optics. And they do contribute a lot for metals, because as you can imagine, when you go to long wavelengths, you primarily have the phonons contributing to this absorption. So the details come from this manuscript. And last, of course, I'll emphasize a very promising alternative method to calculate Phonon-assisted optics developed by Zacharias and Giustino. And it's a very smart method. Instead of doing second-order perturbation theory, where your two perturbations are photons and phonons, what they discovered is that you can do a direct calculation and incorporate the phonons into your starting Hamiltonian, into the structure itself. So they discovered that a single supercell, single optical supercell, where you multiply your unit cell by an integer number, and then you displace the atoms according to a specific linear combination of the vibrational modes. So your structure now incorporates the electron-phonon Hamiltonian. And then, so because you incorporate it, you can only need to do first-order perturbation with direct absorption. And again, you get excellent specs that match experiment to an amazing degree as well. I want to mention some advantages here compared to the second-order method, is that this method also avoids the divergence that we have in Phonon-assisted optics when you are in the direct gap region. The previous equations have this problem that if your intermediate state becomes real, then the equations diverge, and you have to incorporate somehow the lifetime of those states to avoid it. It also avoids the info interpolation, and also gives you the temperature dependence of the eigenvalues and the band gaps, as well as this long Urbach tail at long wavelengths. One other process that's very appealing to me, at least, is that we have many methods to calculate constant structure and direct optics that can be generalized for other functionals, for some which, for example, we may not have the density function perturbation theory implemented. For example, we can do hybrid functionals, you can put van der Waals functionals, you can do excitons. So it's a very general method, and the details in this very nice technical paper in Physical Review B. All right, so this is the summary of the story so far. And of course, I'd like to acknowledge the funding sources as well as the collaborators, both in doing the science and implementing the code. And we'll practice more this afternoon to do some of these calculations yourself. And with that, I'd like to and thank you very much.